Okie dokie. Wow. Some color chalk. Yellow will be good. Okay. Do you think we can start or should I still wait? We reduced in amount of students. If this will continue, that's fantastic. Next time I'm here alone, so. Okay. Okay, I posted some material to this Moodle. Did you check it? So I put the lecture script which I am following. So I copied the chapter from the script I am following, so it's placed in the Moodle. And I will also put today the homework sheet, and then we will discuss the homework sheet. Now I think it's working, right? So then I will also put the homework sheet such that we can discuss it. And my idea would be that maybe next week, or I will make my mind whether the next week or how to do it. I'm thinking to really make the homeworks here. So you will solve the problems on the blackboard. So you really need to solve the problems and present them on the blackboard, because this is the way how you will learn the things. And also, so it would be like that maybe next week I will give just 1 hour lecture, and then 2 hours I reserve for solving the problems in the sheet, okay? So you need to really look and present it. If you don't present, then we are sitting here 2 hours, okay? So it's up to you. So you can visit me if you have discussions, or you can make a small groups or something and you can solve it together. But it's important that we discuss, because there is some physics which I want to discuss then for these problems. And also, yeah, it keeps you for that problem. Okay, so let me just make the summary of what we did the last time. Okay, so we finished with something what is called the Lehmann representation. So this was the endpoint for the last time, and from today we will go on today. So this is for the plan today. Something others, but let me make the once more because last time was some, I don't want to tell it confusion, but there was some uncertainty about this theta function and this delta and other things. So let me clarify these things. Okay, so just to remind you, I will try to make the picture and show the time scale. So let's say assume that this is the time going on. Okay, so this is the time axis, and what we are assuming is that the minus infinity, we are having some unperturbed systems. I'm just drawing it like that. Okay, so I am having some my solid or some, I don't know, other system. I know it's Hamiltonian 8-0, and I prepared the density of state, which is the equilibrium density of state at given temperature T. Okay? And now the time is going, and system is, I don't know, just evolving, and now assume. So that was the things that we are assuming that at some point, I don't know, it can be any time. So at some time tau double prime, I'm just quoting it like that. It's arbitrary. It can be also very close to minus infinity. So we are assuming it that at that time what we are doing is that our system is evolved. And at that time we are taking some perturbation. So we are turning on the perturbation. And let's say I'm drawing this perturbation that I am taking the hammer, for example, right? And I'm heating my system, bam, and the time, and the system starts to evolve, okay? So at this time I'm applying the perturbation. So this is this perturbation at time t. Okay, this is this hammer, is this operator. I hit particularly, let's say, in this corner, so R is really where I'm hitting the system by that, yeah, and the system starts to evolve with this perturbation, and I don't know, during the time I can hit it many, many times or somehow like that, and what happened is that system is now, you know, perturbed. So the system is perturbed, I don't know, it's vibrating, and it's going on, and I don't know, this time function, how I am hammering, and where I am hammering, so first I can hit it here, then I can hit it here, then I can hit it here. There was this function, which we call this, I don't know, I call it H, R, tau. Yeah, this was the function which tells us how I was functionalizing my hammer. Okay, and let's assume that, let's say at time t tau, how I call it, okay, so this was just like that, okay, this is the time tau prime. I assume I stop to use the hammer. So this function is now 0, okay? And now the system is evolving, perturbed, it's going, and again it's evolving. And at this time, let's say, at time 0, what I'm doing is that system is coming to me in the time axis, and now I'm making some measurement. And that was this operator A, which I denoted. So you take something, you apply it at some point R0, and you were measuring something, I don't know, maybe local density of state, so you put it to your computer, and you recorded something. That was the measurement you did, okay? That's the situation which we did. And this function can be arbitrary function. You can hit it just one, then it will be just the delta function, or you can do it periodically, okay? Or you can do it randomly. So this is this arbitrary function, okay? Are you fine with me? Can I go on? This was what we did last time. Okay, and what we did, we compared this situation if I'm not hammering at all. So what we did was that I again prepare my system in the minus infinity, like this, right? And I was not applying any operator O. In this picture, the hammer. The system just evolved. And again, at time 0, I was measuring the same quantity at the same point. So I take the same chip or something. Okay, and I again connected it to my measuring device. I'm just denoting it like that. So this is the screen of the computer. Okay, and you measure something else. And what we did, we take the difference of those two things. So we take the difference of these two measurements, and this was this delta A. This was the difference of these physical quantities. This physical quantity in principle depends on the position when I measure, right? This depends on the time in which I am measuring, right? And we found that these things can be represented as the integral from minus infinity to point tau 0, integral over the tau, the integral over the space. Okay, so going over the volume of my body. And here was these things which we call susceptibility. And I'm just assuming that my system is now homogeneous. So that's why it depends like that. And it is tau 0 minus tau. And there was this function H, R, and tau. Okay? Great. Okay, and then I can put also that this depends on which quantity I measure and which hammer I attack the system, okay? These things depend what I'm using, okay? If I will use the drill, then operator O will be different, and if I will measure something else, then operator A will be different, okay? Great. And this thing is called this generalized susceptibility, and what we did was the following trick that, okay, so we said, oh, let's go to infinity, and what we did here, we preserve the integral, but we just put it here a theta function. Right? That was just the conventional trick that, okay, instead of going to t, I can put here. So now my susceptibility would be this object before plus this thing, okay? And just to give a meaning, and then just to give a meaning, what is this? So this generalized susceptibility and this time difference. So let's clarify that. And oh, Wunhao print something for me, but I see that the color was not good. Okay, no problem. So what is just let's look on the interval, what is this T0 minus tau? Yeah, let's say the tau is somewhere here in this interval. During the perturbation. So tau 0 minus T is this thing, right? This thing is T0 minus tau. Alright, so we see that if this thing is positive, then I can have some response. If this time would be negative, let's say if my tau would be here, then tau T0 minus tau would be negative, and this means I cannot have anything because this theta function is killing this thing, right? So measurement should follow after the perturbation. Yeah, if I measure before the perturbation, I should not have any difference, right? Because at that time they are both still not perturbed, right? So what we are saying is that exactly this thing is like that. That is susceptibility as a function of time. Since it just depends on the time difference, I can just call it as a time. Is like that. It's 0 if time is smaller than 0, and it's something. So I can write it. It's non-zero. In principle, non-zero, right? It can be also 0 for t larger or equal than that. Okay? So this is just the summary in some picture which we have like that. Okay? So this is the refreshment, and now I was also introducing this convergence factor delta. Just I want to once more clarify it for you because it's important, and in some books they are just putting it by hand and some people are confused by it, so I want to once more remind you about that. Okay, doc. So this is the first reminder. Can I clean it? Someone is taking photo? Okay. Great. So hopefully I will not appear somewhere on YouTube or something. Okay, great. So this is the reminder what we did on some picture and about the theta, and because then Woon Hao approached me after the lecture and I want to clarify this point that nothing to worry. Good. The second thing is this convergence factor. Which is just the thing which we are doing to make the calculation much easier, because some integrals are existing. Otherwise, they are also existing, but one need to do, let's say, theory of the distribution and things like that. Okay, so let me once more write it. So what we derived, last time I'm again repeating it, R0, T0 was some integral over from the time, okay. Oh, sorry, the tau. Now I can write it, okay, I am always writing it like that, and then I'm always reinstalling all these things. DDR, great, and then we are having this generalized susceptibility, and I have it R0 minus R, T0 minus T, and there was this function H, R tau, okay. To allow better functions, to enlarge the number of functions which we can use, we said, okay, we can do the trick that we will add here a to the delta tau, with delta, which is a positive quantity. In principle, infinitesimal is enough. So it's infinitesimal. You see, it should have the dimensions of 1 over time. This I'm not writing, but the important thing is it's a positive, okay? And then we see that, okay, if time tau is going to minus infinity, basically this thing is rapidly going to 0 and kills anything unwanted or something like that, okay? Great. So that's what we did. And now what we can do, we can just rewrite this a little bit, and I can rewrite the same thing. I am just rewriting it, and I can just write it as a, and I can write it as a minus delta T0 minus tau plus the tau, okay? You clearly see that this I can do, right? This I'm adding this minus term and then I am adding a plus term, right? And this is just rewritten like that. Okay, so I can do this, perfect. This thing I can take out of the integral. So I'm writing as a delta tau 0, right? And what I even can do now is that I can put here, again, my favorite plus infinity, but I need to compensate for that I'm putting there a theta function, DDR. So first, don't forget theta function, because I changed the integration boundaries, and then I can write this as a chi 0, okay, AO, okay. And this is R0 minus R, tau 0 minus tau. And then I can write this as a to the minus delta T0 minus tau, okay? And then I can write my function HRT. All like that. And now this is the object which we will go on. Yeah, it just really depends on the time difference. So you see that why I did this trick was that now everywhere I have this thing, okay? It's a difference of the time. So I will define this as an object which you should then do make the Fourier transformation. So this is the, I don't know how to call it, but basically this is the things which we are doing the Fourier transformation of and which we are always playing off. And then at the end we are making the limit delta going to 0. Yeah? So this is something, I don't call it new, I can call it the new. Okay, so, or practical, that's the things which really we are able to calculate. This guy, sometimes we are not able to calculate, that's, I am just telling you, because it's not converging properly. And then you need to do some mathematical massage and put some physical inside. But this thing is always well done. So this trick is making things that, okay, this integral we are able to make, okay? So this is the susceptibility which we will massage on from now. So it's always like that, but I'm showing you the way how you can arrive to that, okay? So there is always this convergence factor added. We derive this. We have a formula for that. You remember? There was this complicated integral and exponents to the minus E80t, you know, and everything in the Heisenberg picture, right? And now we need to put a small sandwich like that and then make the Fourier transform, okay? So this is the way how to do it. We can maybe put here a delta. This tells us that the delta is included, and for that we need to make the Fourier transform, okay? So from now on, and I think this was the things which, okay. Then maybe I can continue here. So for Fourier transform, then we take this object and we make its Fourier transform. Ft, I will just denote that it's a Fourier transform, okay? So the Fourier transform of that, okay, it can depend on, we can make also the Fourier transformation in this variable, but okay, for now it's not important. I'm just writing the Fourier transform with respect to the time, and so that's, I'm just putting a time difference here, or frequency of that. So this thing is by definition, okay, integral over the time. So I should go from minus infinity to infinity. I'm now doing the Fourier transformation with respect to t. This variable I can call t because it's just one variable. It's not the function of two variables, it's just function of one variable. And I'm taking this chi nu blah 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 as a function of t. Okay, there can be other arguments, and then I'm taking a to the minus or plus e omega t. Okay, if I'm just considering the Fourier transformation. And this thing, we are plugging what I said before. So we are plugging here theta function of t, right? Then we put something what we computed before. Okay. And then we are putting this convergence factor to the minus delta t, right? So this is the object that you should do the Fourier transformation of. Okay. And if I'm making the Fourier transformation, this theta function is doing the things that I am just basically integrating from 0 to infinity. Okay. And then I have something to the minus delta t. Okay? So such integral. And such integral, this is the convergence thing, that if time is now going to infinity, then this minus thing is killing it. So the integral is existing. Okay, so this is the things that help us to make the existing of some integrals which otherwise are not properly existing. Okay? Guys, are you fine? Can I consider we understand each other? Even I speak broken English. Can I go on? Perfect. So that's the clarification, what we did, and summary. And now we will continue. And I will continue from the Lemon representation. So I think last time we derived this Lemon representation. And just please correct me which I already wrote directly the Lemon representation in the Fourier transform, or it was just in the time domain, or did I write this formula? I hope I did. That we have something what we call spectral or the Lemon representation, and I hope I wrote this formula. And if not, then please correct me. It's 1 over z, right? And there was the sum over the n and m, which are the, and there was a to the minus beta n minus a to the minus beta m. Then we had this h bar omega plus an minus am plus this e delta, because I was already making the Fourier transform. And then we had the matrix elements of the operator A and the matrix element of the operator O. And everything was in the Schrödinger picture. Which was, yes, Danny? Yes, Danny, you're right, it should be. Yes, sorry. Please always correct me, okay? Just if you see that I'm making mistake which makes you unsure, don't wait until the end or something immediately, okay? And also if you have questions, please immediately stop me and ask for clarification. Chapin, okay? Good. So this formula was written, right? Okay, great. So we finish here, and now I am following from that point. Good. So then let me clear the rest of the blackboard, and we start to a little bit massage that, and we go a little bit. Okay. Now I want to, okay, let me clean and then let me write. Okay, and now I want to use one identity, and I hope, if you didn't have it, then I will put it to the sheet, as I just want to ask you. There is a very important identity in mathematics which has a name. This depends on the nation from which you are. Cauchy, and I don't know, maybe there are other names. Theorem. And it's written like that. So I just write it and you will tell me whether you know it or not. Did you see it before? It tells about some integrals, that if you have the integral, so it's written like that. But main meaning is for the integrals, that if you compute the integral from minus infinity to infinity of the following object, so you have some function fx, and then you are having something like that, and you integrate it over the x, then this thing is telling you that this integral can be computed like that, that you take the principal value of this integral, which means the following thing, that you take the integral from minus infinity to infinity, and you take something like that, which is the x square plus epsilon square, and then you are getting x, fx dx. This is this principal value of 1 over x. And then you are getting minus, and you get the integral, in principle, EP epsilon. Oh no, it's epsilon already in the limit, and this is the value of the function at point 0. Did you see it in some form? This is in the limit. If you calculate such integral and you make the limit epsilon going to 0 of such integral, this is the same as calculating this integral and making the limit epsilon going to 0, and there will be a delta function of that. So you are silent. Does it mean you hear it, you have it or not? You shouldn't feel shame that you don't know it, but I just need to know whether you know it or don't know it. So who knows it? A part of me? No, who doesn't know it? Okay, this was the check. Great. So I will put something to the homework sheet that you will read. But this exactly means like that. So that if you calculate such integral by brute force and then you are making limit epsilon is going to 0, the thing is that you cannot make the order, you cannot change the order of the integral and the limit. So firstly you need to evaluate this and then you make the limit, and this is the claim, okay? And it's conventionally in many books it's written like this. Okay, so I will use it today. Even you don't know it, I will use it just once, okay? But it's important for something which will follow, okay? Good. Okie dokie. Okay, and the immediate application of this. The other things, by the way how to do it, the best way is also to use quite nicely, this is explained in the Wikipedia, by the way. So you can look for the Wikipedia, and there is a page about that, and it's, I would say, quite nicely explained there. Okay, but if I am now applying this theorem to this formula, which we derived the last time, this is exactly assigned like that. Okay, here it's E delta, here it's E epsilon, but this doesn't matter how you call the variable, okay? So if you now apply this theorem to this, you can immediately write what is the imaginary part of that. So what we can write here is that the imaginary part of this susceptibility as a function of omega, you can clearly see that, okay, imaginary part of that, if delta is going to 0, which we said that we should always do at the end of the calculation, then we see that result of this is just 1 over, oh, it's a minus p. Okay, this is this p. And now we are taking this function 1 over z. And this is the sum over nm. And then I'm getting here a to the minus beta n minus n minus beta m. And then there would be, we don't have any, nothing. Okay, I can put z here. Okay. And here I have these matrix elements. N, A, M, M, O, N. Okay. And then I have this delta function, h bar omega plus n minus m. Okay? So I'm just basically converting this object to delta function. You see what happens. Nothing changed, only this object was turned to the delta function. Okay? this minus p is here, and I'm writing the imaginary part, so there is a minus p. Minus p, like that, okay? Fine? You don't see it, Chapin? Yeah, you have a question? Go on. This is the partition function that we derived the last time. The z was sum over n e to the minus beta an. That was the partition function, canonical partition function. Yeah, that was exactly said like here, that if you have the such thing, and if you now take the imaginary part of this thing, then the imaginary part of this thing is just this thing, right? So I'm just using this thing, plus and minus, and minus sign. So that's what I was using. Is that fine? Yeah, but this one is a real. It's a real function. You see it from here that if fx is the real function, in our case here fx's function is the one in principle. It's written like hidden like that. Yeah. So this is a real thing. Okay. Okay, and since I have a delta function here, I will just rewrite it a little bit, because if I have a delta function here, basically what I can do, and people are normally see it, and you will see it, I will just write the result and you will clearly see it. So we can just rewrite the same thing in the following form, that it's a minus p. Okay, now I will put z here. Sometimes I'm putting z there, sometimes there, but this is just a constant. And I can rewrite it in the following form, that it is 1 minus e minus beta h bar omega, okay, and then I have a sum over n and m. Maybe we will use it at some point, that's why I'm writing it. Or you can also find it in the textbooks or in the notes. Okay, and I will also explain why I wrote it like that. So because what I can do it here, for example, I can express em from this expression, since it's a delta function, so it's non-zero only in the case when em is equal to h bar omega minus, plus en. Oh no, I did it differently. Let me just tell you what I did, how I massage it here. So what I can do from this exponent, I can write this exponent as a to the minus beta an, and then I'm writing it as a 1 minus to the minus beta am minus an. Okay? You see? Yeah, I was just like that. And now I'm using the fact that m minus n is, or I can do this, that I could put a plus. Here I'm getting minus and plus. This is also fine, right? And now I'm using the fact that n minus am is equal to h bar omega. So the next step is that I'm writing this as a minus beta an. And I'm writing this a minus a to the beta h omega. And now I was taking here that this guy is here, and this guy is taken out. Sorry, but here it should be plus. Oh, but why I have a minus? Then I'm doing something wrong. No, it's a minus. An minus am is minus h omega. Sorry, so here it's a minus. An minus am, if this is equal to 0, is equal to 0, then it means that an minus am is minus h bar omega. Okay? So there is a minus. Okay, great. And this thing is then coming here. Okay? Danny, everything okay? Give me some signal, some smiles that, oh, I understand, because I see you so serious, you know, like just being me, and I don't know, they don't know, or I don't want to lose you. If I lose you, then, you know, not good. Can I go on? Great. The special case of this, so this is the general, and now let's discuss the one very special case, and I will erase this and I will write the special case here. So the special case of this formula is the case when I would have two operators, and this we will see later several times. That's why I'm a little bit spending time on that. Okay, so I explain how I got it. I explain all those things. Great. Okay, I can erase that. And we can go to the special case. And the special case would be the case if I would have the susceptibility of the case that there is operator A and operator A dagger. Here the special case that O is A dagger. And then this is a function of omega. We clearly see what is the, why we did it. Here, omega enters just in the delta function, and all the dependence on omega is here. Yeah? So here in the special case, what we are having is that it is a minus p divided by z, and there is 1 minus a to the minus beta h omega, and then I have this summation over n m, and now in that case, I would have O is the same thing as A dagger. So basically, I can write it in the following way. Because if I put a dagger here, right, then I can use the fact that I can, yeah, so that's what I was doing, and now I'm using the fact that this is the same as n a m complex conjugated. So complex conjugated and non-complex conjugated is the absolute value, right? Okay, so that's I wrote it. And now it's a nice thing, and that's why I want to say is this is a nice thing because this is always positive. So if you look at that, this is always positive quantity. Right? And this thing is for omega larger than 0 and for omega smaller than 0 different, right? So for omega larger than 0, this is, oh, and I will also include this minus sign. So let's also include this minus sign to that. So now we are seeing that if omega is larger than 0, then this thing is smaller than 1. So the difference between 1 and something what is smaller than 1 is positive because it cannot be negative. But there is this minus sign. So we see that this thing is then the negative. And for that it's always positive, right? Do you see it? Okay, now I'm coming to the main conclusion of that. Is that, and this is nice thing about that, and we will have the example in the homework sheet, that if you now multiply omega times imaginary part of the susceptibility of that type, and I have here a minus? No, I have, okay, and if I put a minus here, then this thing is always larger than 0. How agree? I agree, so I think it's enough to agree. And you should see it. Do you see it? Everyone see what I wrote? It's here, because this imaginary part is also having this exponential. So I'm thinking that all these things together is this. If I will multiply it by omega and minus, then it would be always positive. Where? Yeah, yes, you're right, sorry. Yeah, I forgot to write this term, yes, thank you. But this is always, it's here.
But I mean the right side.
Where right side?
And put
Here it should be a to the minus beta n. Yeah, right.
And it also
It's positive to positive because this is always larger than, it's always positive number, right? Yeah, thank you. Good point. Okay? Good? Guta, guys? Great. And why I'm pointing to that? In the homework sheet you will have a problem, and we will see, you will have a problem because you will need to sheet the homework sheets, okay? So you have really, there will be problem and you have a problem because you need to solve it. But you will see that the dissipation of the energy in the system, there is a homework task. This is called the fluctuation dissipation theorem. I leave it as a homework for you. Basically, you will see that what happened during this process of the hammer, you are hammering something. I draw the picture. Then you are giving some energy to the system. Because it's not for free, like you are exchanging some energy with the system. And you will see that during this process of doing this perturbation, you can compute what is the change of the energy of the system as a function of time. And you will see that this is proportional exactly to this thing. For some special cases, which is always larger than 0, which means that the system is getting the energy. So see the homework problem, okay? Good. So before the break, let me just write two important relations. Okay, I think this was clear, right? Was it? You got it. So we realized that as a function of omega, the imaginary part is having quite simple formula. By the way, this formula is also related to something which you maybe know, which is called the Fermi-Golden rule. Maybe you don't see it, but in the Fermi-Golden rule, you are exactly having this guy. There is some Fermi-Golden rule hidden also here. So I am now still didn't make the connection, but I will then explain it or later, okay? But I'm just telling it. So that's a little bit spend the time of that because it is quite general, and this important thing is that because this is larger than 0, it has some also connection to physics that is tell us how the energy is changing with the time of that. Okay, and now I will want to just write very important relation, which is called, did you hear it? Kramers-Kronig relation. Okay, so this is also a very important thing which I will just write because we will use it at some point, and it's again something general. So it's important to know it. Do you have question to that? No? I'm doing now Obama, having eye contact with everyone. Okay, go. Then I'm cleaning the blackboard. Good. Again, we will use the things about the imaginary part. And again. Okie dokie. My notes are here. Okay, we have this imaginary part, this theorem. Pity you didn't have it, okay? But as a consequence of that, or should I do it or not? Okay. So or will I give it as a homework?
let me think. Maybe I can give it as a homework. Or I will just write the formulas and okay, so why I was telling this, maybe I forgot to say it. This imaginary part of these response functions are playing important role because it's really connected to the experiment. So I was right, I wrote it and you will have it in the homework problem that I showed or I claimed that the change of the energy is proportional to the minus omega imaginary part of the, for example, this response function. And this is exactly the things what you can do in the experiment. So you can really measure in the experiments how the energy is changing in the system, let's say by some spectroscopic measures or by calorimetric measures or somehow. So you will get, in principle, experiment, out of the experiment, you are able to extract how this quantity depends on the frequency. You are perturbing system with some frequency, you can perturb it with different frequencies, you can measure responses, you will compute or measure how the energy is absorbed by the system at given frequency, and you can get this information about the quantity. So these experimentalists can you do, and as a theorist, you can have your own theory, and you can compute this quantity, and if it's matching, then your theory is explaining the experiment. Yeah, but there is also other thing why this thing is important, because if we are able to measure this quantity, there are very important relations which are called Kramers-Kronig relations, and these Kramers-Kronig relations are given in the following form, that if I just know and this thing is general, and it has a name as a Kramers-Kronig relation. And the claim is like that: if you know imaginary part of the susceptibility AO as a function of omega, then the claim is that you know the whole Ki omega. And the claim is like that, or the theorem is like this. Integral of that is equal to minus 1 over P, and this is the integral from minus infinity to infinity d omega prime. This is the integration variable, and this is omega minus omega prime plus E delta imaginary part Ki omega prime. The proof of that is very easy in principle. You just take the imaginary part of that, which we derived last time, which we wrote it before. You take the spectral representation, you take the imaginary part, you plug in, and then you use this Sokotsky-Plemé theorem for the real part and imaginary part, and you discover that it's exactly this thing. So I will put it as a homework problem to the sheet, because let's say it's in principle boring calculation or straightforward calculation, but the result is very important. So this is the thing, and maybe we will really encounter it somewhere, but this is the practical way how to compute from the response function which you measure in the laboratory. This is this thing. You can construct the full response function. So it's a very useful formula. Okay. The proof of that. How many of you had the integration in the complex plane and heard something about the Cauchy theorem and the residuum theorem? Did you have the complex analysis a bit? Cauchy theorem, residuum. So this comes from that, actually. If you know it, it's immediate consequence of that. But I am afraid that you didn't have it, so that's okay. To prove this, it's not difficult. Just really take the imaginary part of what I did, plug it here, and use this formula. And you will see it's giving full thing, okay? So I will stop here now, and we are having another break. Okay. Good. Can we make also this aircon working, or it's working or not? Thank you, Danny. Wow. Or we are having break later or now? Like, I'm confused. It's 50 minutes and then break, now it's break, or it should be break in 10 minutes? It's now break, okay.